Here we've got a system of differential equations represented in matrix form. Derivative of some unknown vector function equals this coefficient matrix, -1, 2, -1, -3, times that same vector function. And of course, we could just write that as dx dt equals ax. And what sort of solution should we expect from a matrix differential equation like this? What kind of solution do we generally expect there? It might help to look at a scalar equation that's kind of equivalent to this. If we have a scalar equation, like let's say dy dt equals, let's say just r times y, where r is just some constant scalar, like maybe dy dt equals 5y or something. What would the solution to this scalar differential equation look like?
Oh.
Or how would you solve that?
I am not sure.
Well, if it's just dy dt equals just something about y, we can always use separation of variables there. The method's from chapter 2, I think. So how would you separate variables in this case?
Would you put dy of y and then dtr?
Yeah. If we divide both sides by y and multiply both sides by dt. At that point, we can now just integrate both sides. And what do we get for the integrals there? First of all, integral of 1 over y becomes
the natural log of y equals rt, excuse me.
Yeah, that should work. And also, since this is an indefinite integral, we should include a plus a constant because we're looking for the general solution, all possible solutions. And then how do we get rid of the logarithm?
Just set it to the e.
Yeah, your e to the power of both sides. So e to the left side equals e to the right side. Logarithm and exponential cancel out, so we just get y equals, and then here we've got e to the power of something plus something, so we can split that up into e to the rt times e to the c, and e to a constant is just some other constant. So we'll call that capital C. So in general, without even having to go through these steps every time, anytime you got dy dt equals a constant times y, you know the solution is going to be exponential, e to the rt times some constant. We can expect a similar solution here. If we've got derivative of x equals a constant times x, the only difference here is that the constant is a matrix, and also the function is a vector function instead of just a single scalar function. But we can make a similar guess. We can guess that the solution is e to the rt times some constant. Though in this case, the constant is not just a scalar, it's a vector, because we need the function to be a vector function. So we'll make the guess that the solution looks like e to the something t times some unknown constant vector. And as usual, how do we check that guess? How do we check if a solution really works for a differential equation? Or what does it mean?
Back in?
Yeah, we can just plug that back in to the original differential equation, which of course means we'll need the derivative as well. But that'll just be r e to the rt times c. So to check that, we can replace dx dt with the derivative of our guess. And we want to know, does that equal a times our guess? And it looks like this is at least plausible. We've got a scalar times a vector. We've got a matrix times a scalar times a vector. These are both at least going to end up being 2x1 vectors, assuming A is a 2x2 matrix. So it seems at least plausible that these can equal each other. Also, what can we ignore in this equation? What could we get rid of entirely?
C. Since
we can't quite get rid of C, because how would you get rid of a multiplier?
By dividing it out.
Right. But you can't divide by a vector. So we can't get rid of the times c since it's a vector. But what can we divide by?
Oh, e to the rt.
Yeah, we can always divide by e to the rt since that's never going to be 0 anyway. And we're left with a matrix times a vector equals a scalar times a vector. Our guess will work. The original guess, x equals e to the RT times some unknown vector, works if and only if the coefficient matrix times that vector equals the exponent times the vector, the R times the vector. And where have you seen this before? What do we call it when a matrix times a vector equals a scalar times the same vector?
Is that linear independence? Or
it's related to linear independence, but it's another idea that's usually presented at the very end of linear algebra. This is called an eigenvector.
Oh yeah, the eigenvector.
You got a vector that when multiplied by a matrix, it acts like just being multiplied by a scalar. Or to put it another way, for purposes of this vector only, the matrix multiplier acts like just a single number. What this means is this guess works if and only if C is an eigenvector of the coefficient matrix and R in the exponent is the associated eigenvalue. And so for that reason, we usually write that as a lambda, customary for eigenvalues, and we'll say this is vector V. So our solutions are generally going to be of the form e to the lambda t times V, where lambda is an eigenvalue of the coefficient matrix, and V is the eigenvector associated with that eigenvalue. Which ultimately means solving a differential equation with matrices like this ultimately just amounts to finding the eigenvalues and eigenvectors and plugging them into this format. Any questions on that so far? And typically, if you've got an n by n matrix, you can expect up to n different eigenvalues and different linearly independent eigenvectors. So if you've got, like for a 2 by 2, we would typically expect up to 2 different eigenvalues and 2 different eigenvectors. So you'd have e to the lambda 1 t times v1, and separately e to the lambda 2 t times v2. And from what you've seen with second order equations in chapter 3, if you've got 2 types of solutions, how would you combine those to get the general solution?
C1 times the first plus C2 times the second.
Yes. So that would be the format we'd expect for the general solution. This also ties in nicely to the idea that any scalar multiple of an eigenvector will also be an eigenvector. So by multiplying the eigenvector by some scalar, we're just generalizing it to all possible eigenvectors, and then multiplying all of them by this exponential function, adding those together to combine those as a linear combination to get all possible solutions. So this is typically the format we should expect for the general solution of a matrix differential equation. And of course, for a larger matrix, you might have more, like if this was 3 by 3, we'd have up to 3 eigenvalues and 3 distinct eigenvectors. So we'd have it also plus C3 to the lambda 3t times V3. Any other questions on that general format? And also, typically, how would you find C1 and C2 if you want a specific solution? What other information would you need?
Initial conditions.
Right. And in this case, the initial conditions would look like the value of vector x at time 0. So the initial conditions might be something like x of 0 equals 3, 5, or something like that. So a specific numerical vector value for vector x at a certain instant in time, usually time 0. So you fill that in, or fill in 0 for t. Note that that makes e to the 0 and e to the 0 both 1. So you just have c1 times one of the eigenvectors plus c2 times the other vector equals the initial condition vector. Again, going back to the idea of a linear combination. You want to find a linear combination of the eigenvectors that adds up to the initial condition. Any other questions on that so far? So let's try that with this matrix. We'll just need to find the eigenvalues, the eigenvectors, fill them into this format, and that should do it. And for the eigenvalues, how do we typically find eigenvalues of a matrix? What would be a good starting point for that?
Isn't it the determinant of A minus lambda times the identity?
Yeah. Exactly. If we take the determinant of A minus lambda I and set that equal to 0, That gives us a characteristic polynomial that we can solve for lambda. So if we write out a minus lambda I, that means we're just subtracting lambda from everything on the main diagonal, since lambda I is just a matrix with lambdas on the diagonal and zeros everywhere else. So we subtract lambda from everything on the diagonal, we get -1 minus lambda, 2 as it is, -1 as it is, and -3 minus lambda. We can use, since this is just a 2 by 2, we can use the multiply the diagonals method for the determinant. So multiply this diagonal, -1 minus lambda times -3 minus lambda, minus the other diagonal, -1 times 2. And we want to set that equal to 0. Multiplying that out, we get 3 plus 3 lambda plus 1 more lambda, so plus 4 lambda plus lambda squared minus 2, or in general, lambda squared plus 4 lambda plus 5 equals 0. So there's our characteristic quadratic for solving for the eigenvalues. And is that factorable? What would that factor to?
1 and 5, right?
Yeah.
1 and 5?
Or excuse me, negative.
5 just would be negative. The problem is that it'd be -1 times 5, which would be -5, not +5. So -1 and 5 doesn't work. Doesn't really look like this one's factorable, at least not with nice neat numbers. So if it's not directly factorable, what else can we do?
Quadratic.
Yeah, let's try quadratic formula and see where that takes us. So -b plus or minus square root of b squared minus 4 times a times c all over 2a. -4 plus or minus square root of, and what does the discriminant work out to here? We got 16 minus 4 times 5. What does that give us?
-4.
Right. We've got a negative value inside the square root, which means we're going to end up with what sort of results?
Imaginary.
Right. -4 plus or minus square root of -4 would be 2i. So plus or minus 2i all over 2. Distribute the divided by 2, and we get -2 plus or minus 1i. So those would be the eigenvalues. We get complex eigenvalues here. -2 plus I and -2 minus I. Any questions on that so far? So that's going to be a bit of a problem because we're going to have e to the power of a complex number. But we've already seen that before. How can you deal with e to the power of a complex number?
Euler's formula?
Yeah, Euler's formula.
Oh, sorry.
Euler's formula.
-2 points.
Right. Euler's formula for converting the exponential functions into sinusoidal functions. So we are ultimately going to get a sinusoidal solution here, presumably sinusoidal oscillation with decay, because we've got also a real part, a negative real part, which means we're going to split this up into e to the -2t, which decays, and e to the plus or minus it, which is going to represent sinusoidal oscillations. So we should expect some sort of decaying oscillator, except as a vector. So it's going to be maybe swirling around the origin, but getting smaller and smaller, perhaps forming some sort of spiral shape. So to deal with that, of course, we'll also need to find the eigenvectors. So let's try that next. Now that we've got the eigenvalues, we can go back to a minus lambda I to find the eigenvectors. Because we ultimately want a times b to equal lambda times b, which is equivalent to saying, if we subtract lambda b from both sides, a minus lambda I times b equals the 0 vector. If we subtract lambda v from both sides and factor out v, we're left with a minus lambda I, because we can't just factor out v and leave lambda as scalar. We've got to have a matrix component also. We now have lambda, so we can fill in a lambda value into a minus lambda I, and then solve this using an augmented matrix. So if we write out a minus lambda I, that'll be -1, and we've got two different lambda values. Let's say we use the lambda value with plus. Let's call that lambda 1. So lambda 1 is -2 plus I. So we're going to write out our original coefficient matrix, and we're going to subtract -2 plus I from each number on the diagonal. Now we want to augment that with the zero vector and row reduce. Of course, the zeros in that final column are not going to change anyway as we row reduce, so we don't even need to write them. We can just fill them in at the end. And make a note of our eigenvalues also. Lambda 1 is -2 plus I. Lambda 2, we're calling -2 minus I. And order doesn't really matter there. You just want to pick one of them to call lambda 1, the other to call lambda 2, and be consistent about it. So we're using lambda 1. We simplify this. We get -1 minus -2. That's -1 plus 2. So +1 minus I. -1, 2, and -3 plus 2 would be -1 minus I. And we've got a column of zeros, but I'm not going to bother writing it because it's going to stay zeros anyway. So we want to row reduce this. The problem is if we take our pivot and we want to use this pivot to cancel out everything under it, that's kind of tricky because we've got a complex number that we're using to cancel out a real number. But how could we turn a complex number into a real number? What operation can you do to any complex number that will make it into a real number? Like if you have a plus bi, what could you multiply that by that guarantees the result will be real?
Was it the cosine plus sine, I sine theta or whatever? Is that what it is?
Well, ultimately, these are going to turn into that based on the Euler's formula. But without even worrying about exponents and cosines and sines, if you've got a complex number, one thing you can always multiply it by that will guarantee turning it into a real number is the complex conjugate.
Right.
In the sense of keeping the same real part, but taking the opposite of the imaginary part. Anytime you multiply a complex number by its own conjugate, when you multiply that out, you get a times a, bia minus bia, those cancel out. And then bi times -bi would be -b squared I squared. But what's I squared?
Just a real value.
Right, specifically -1. So we get a squared minus b squared times -1, which is just a squared plus b squared. This is also, by the way, how you calculate the magnitude of an imaginary or a complex number. Multiply the complex number by its own conjugate, and then take the square root of the result. And that'll tell you the magnitude, which is essentially like absolute value for complex numbers. Square root of the value times its own conjugate. That would be how you calculate the magnitude, like how the size of the imaginary number or complex number. So what we can do here, if you have a complex number that you'd like to turn into a real number, so you can use it to cancel this out to get reduced row echelon form, we would multiply not just this number, but the entire row by its complex conjugate. So that's what we're going to do here. We're going to take the entire row and multiply it by 1 plus I. That at least guarantees that the first number becomes positive or real. And positive as well. So 1 minus I times 1 plus I, we get 1 times 1. Minus I and plus I cancel out. Minus I times I is minus I squared, which is plus 1. So the first term just becomes 2. which also is the magnitude squared of this complex number. So its magnitude would be square root of 2 if we need that. And of course, this 2 also gets multiplied by 1 plus I. So we get 2 plus 2I. And then -1, -1 minus I, we're keeping the same. Also, for convenience, now everything in this row is all multiples of 2. So I'm going to multiply that whole row by 1/2 just to make the numbers a little easier to work with. So we get 1, 1 plus I, and then the second row, -1, -1 minus I. So we've now at least gotten to the point where the entire first column is all pure real numbers. If there were more complex numbers, like if this were a larger matrix with also other complex numbers, you could just multiply each row by the complex conjugate of the first thing in the row, and that'll guarantee the first thing becomes a real number. In this case, though, the first column is now all real numbers. How can we cancel out the -1 in this second spot here? Because remember, for reduced row echelon form, we want each pivot to be alone in its column.
You just, excuse me, add the first row to the second.
Yeah, if we modify the second row by adding the first row, then not only that -1, but what else happens to the second row? What's our new second row going to be?
Would it just be 0, 0?
Yeah, all zeros.
Okay.
So this is now completely row reduced. Each pivot is a 1 because this is the only pivot now. The second row has no pivot. So the only pivot is a 1 and alone in this column. This is now fully row reduced. And in fact, we should generally expect this to happen. When you're finding eigenvectors by row reducing the matrix, you should expect at least one of the rows to cancel out to all zeros. Because a matrix has infinitely many eigenvectors, so we should expect infinitely many solutions. And that happens because one of the rows cancels out. If none of the rows cancel out, that means something has gone wrong somewhere. But now that we've got this in reduced row echelon form, we can use the remaining row or rows to figure out the eigenvector. So let's say our eigenvector, let's just call this AB for the moment. And remember, we had an extra column that we've been ignoring. This really should have an extra 0, 0 at the end. If we write out this top row in terms of A and B, we've got 1 times A plus 1 plus I times B equals 0. And at this point, we could solve for one of these variables in terms of the other. And which of these would be easier to solve for, A or B here?
Would it be A? Or
Sorry, what was that?
would it be A? Or...
Yeah, I think A would be easier to solve for. All we have to do is subtract this term from both sides, so we get -1 minus I times B. And if we fill that into our vector AB here, we can just replace A with that whole thing. A is -1 minus I times B. And then we could factor B out of this, because B now shows up in both terms. So we could factor out B, and we're left with -1 minus I, 1. So this is one way of writing the eigenvector. Any questions on that so far?
Not necessarily a question, it's just a comment. So Dr. Tab, when we got to this section, he basically said, so you have A times vector V equals 0, right?
Mm-hmm.
So he took vector V and said it was A and B. And then basically, when you get to, you basically multiply that out. So you'd get, A times 1 minus I plus 2B equals 0, kind of like just set that up. And then he basically said that you just pick an A, right? So like usually he picked 1 for A. Mm-hmm. And so A would be 1. And then for the second part, you would just use the equation to find for B. That's just how he did it.
Is this for finding the eigenvector?
Yeah.
Yeah, there's often multiple different ways of finding the eigenvectors.
Okay.
So they should all end up with the same result, though. Well, not exactly the same result, because notice that B could be anything, as you said. So any scalar multiple of this vector will work. In fact, b doesn't even have to be a real number. We could make b an imaginary number and this would still hold.
Okay. Because I got, doing it that way, I got that v1 equals 1 over 1 and then I minus 1 over 2 for the other.
Usually it's not a good idea to have complex numbers in the denominator though. So you'd want to realize that by multiplying the numerator and denominator by the complex conjugate.
Okay, I see what you mean. But yeah, it was just 1 is the top of the matrix, and then the second part of the vector, excuse me, is I minus 1 over 2.
And we could actually accomplish that as well here by, again, we could multiply by any scalar, including complex scalars.
Cool.
So if we do that, if we take -1 minus I1 and multiply this whole thing by the complex conjugate of that top number, which would be -1 plus I, then the top number is now going to become pure real. In fact, -1 times 1 is 1. I times I is +1. So we get 1 plus 1, that'll just be 2. And then 1 times -1 plus I is just -1 plus I. So this would be an equally valid alternate way of writing the same vector. Or not the same vector, but a scalar multiple of that vector, which could also be used as the eigenvector. In fact, I think this might be a little easier to use just because of the real number in the top coordinate. Well, not necessarily easier, but maybe a little more convenient for certain purposes. In fact, let's go ahead and use this as our eigenvector. We got λ1, the first eigenvalue is -2 plus I. And then the associated eigenvector, let's just call 2 -1 plus I. So we have λ1 is -2 plus I. And the corresponding eigenvector v1 is 2 -1 plus I, at least as one way to write it. Any other questions on that so far? And for the other eigenvector, instead of going through the whole process again, we can use a very useful shortcut. What do we know about the eigenvalues? How do those relate to each other?
Conjugates.
Right, they're complex conjugates. And in general, if the eigenvalues are, let me clarify this, for a real matrix, if the matrix is pure real, and you get eigenvalues that are complex conjugates of each other, then the eigenvectors also have to be a complex conjugate pair. So we can say λ2 is just the conjugate of λ1. That means v2 should be the complex conjugate of vector v1. In other words, we keep the same real part, which is the 2 and the -1, but we take the opposite of the imaginary part. So plus I becomes minus I. So that gives us our second eigenvector, or at least one way of writing our second eigenvector. Again, any scalar multiple of that will also work, including imaginary scalars. So we now have λ1, λ2, v1, and v2, at least one way of writing them. And we should now be able to substitute those into our general format and see what happens with Euler's formula. So let's try that. If we fill those in, we've got x equals c1 e to the -2 plus I t times v1, which is 2 -1 plus I, plus c2 e to the -2 minus I t times v2, which is 2 -1 minus I. And right away, it'd be a good idea to split up those exponentials because we've got complex exponentials. Let's split those up into pure real and pure imaginary parts. For instance, the e to the -2t plus or minus it. We can split that up into e to the -2t times e to the plus or minus it. The e to the -2t, since it shows up in both terms, we can factor out. And we can just leave the e to the -2t as it is, because that's pure real, so that's fine. So let's start by doing that. We got e to the -2t times whatever's left. Specifically, what's left is going to be an e to the it or e to the negative it times each of these. So e to the positive it times c1 times 2 negative 1 plus I plus e to the negative it times c2 times 2 negative 1 minus I. So we've split out the real exponential, and what's left, what can we do with the e to the it and e to the negative it? What would, or how would you expand e to the it using Euler's formula?
That would be cosine theta plus I sine theta. But I mean,
well, in this case, theta would just be t. If it was like e to the 3it, then you have cosine of 3t.
Right.
But since it's just e to the I times 1t, it's just cosine of 1t plus I times sine of 1t. And likewise, e to the negative it would be cosine of negative t plus I times sine of negative t. But since cosine is an even function, a negative on the inside can be ignored. And sine is an odd function, so a negative on the inside can be brought out. And we get cosine of t minus I sine of t. So we can make those substitutions. Also, since we're going to have to write cosine of t and sine of t over and over and over again, let's make a substitution there. Let's say cosine of t we'll just write as capital C, and sine of t we'll just write as capital S. And then we can fill in cosine t and sine t at the end. So that looks like e to the 2t times e to the it becomes capital C plus I times capital S. And those are both going to get multiplied by C1 and this vector. So C1, I'm going to distribute the C1. C1 times cosine plus I C2 times sine. And that gets multiplied by the 2 and the negative 1 plus I. And likewise, e to the negative it, that's going to become cosine minus I sine. And oh, that should be a C1 there, shouldn't it? So those will both be multiplied by C2. C2 times cosine minus I times C2 times sine. And all that gets multiplied by 2 negative 1 minus I. Any questions on that so far? And there are several ways to proceed from here. What I usually do is multiply these together, combine everything into just one colossal vector, but then split it up into a pure real vector plus a pure imaginary vector. Because everything in here is going to become a complicated tangle of real and imaginary parts. Those tend to be much easier to deal with if you can split it into a pure real part plus a pure imaginary part. So let's go ahead and multiply this out. We're multiplying this C1 times cosine plus I C1 times sine. That's getting multiplied by the 2 and the negative 1 plus I. So that gives us 2 times the whole thing. So 2C1 cosine plus 2I C1 sine. And then the lower coordinate, we've got this whole thing times negative 1 and this whole thing times I also. So the negative 1 just applies a negative to both of these. Negative C1 cosine minus I C1 sine. But then multiplying I by each of these gets an extra I on the first term. So I C1 cosine, and then I times I becomes negative 1. So that becomes a real term, minus 1 C1 sine. And then for the second part, we've got plus this whole thing times 2. So 2C2 cosine minus 2I C2 sine. And then for the lower coordinate, this whole thing times -1 and times -I. So -1 multiplied by both of these just flips the sign, minus C2 cosine plus I C2 sine. And then a -I multiplied by the first term becomes -I C2 cosine. And minus I times minus I, the minuses cancel out, we get I times I, which is -1. So it's still negative C2 sine. And that gets a little messy there, but keep in mind this last bit is part of the second coordinate. So that's just one line and then the other line. So it's a huge mess, but we can now split it into the real parts and the imaginary parts. Any questions on that step before we split it up?
Just so I'm clear, the second line in there is all part of the first row, right?
This is the first row. I mean, it's not even rows. This is the top number.
And what's underneath that? Is that the first column of the second row?
There's only a single column here, though, because remember, we just have a single 2x1 vector. We multiply a scalar by a 2x1 vector, we get a 2x1 vector. Okay. We add it to another 2x1 vector. So this whole thing on top is just one number.
Gotcha.
It's just got several terms added together. And then this whole thing is the entire second number.
Okay.
So again, it's a colossal mess, but this is just two numbers. The top number of the vector and the bottom number of the vector. Essentially the x coordinate and y coordinate of the vector function we're talking about. Oh, and of course, there's still the times e to the 2t up front that we don't want to forget. So let's see if we can split this up into real part and imaginary part. For the real part, if we take a look at just the real terms, we've got 2c1 cosine. That's imaginary. 2c2 cosine. And then that's imaginary. And then the lower coordinate, we've got -c1 cosine. Imaginary, imaginary, that's real, -c1 sine. -c2 cosine. And -c2 sine. So that is the real part of the solution. Again, times e to the, should be -2t, e to the -2t, attached to the whole thing. But we can fill in the e to the -2t at the end if we need to. And then the imaginary parts, we've got 2i c1 sine. And everything here is going to have an I in it, so I'm going to preemptively factor out I. So 2c1 sine minus 2c2 sine and then the lower coordinate, we've got -c1 sine, positive c1 cosine, positive c2 sine, and -c2 cosine. So that's our pure real vector and our pure imaginary vector. However, we may be able to factor this. What do you notice about both of these terms here?
They're both cosine.
They're both cosine.
And they're 2.
And they both have the 2. So we could factor out 2 cosine. We're left with just c1 plus c2. So the entire top term here can be written as c1 plus c2 times 2 cosine. Can you factor a c1 plus c2 out of this also?
It would be minus, wouldn't it?
it might help to group them together first, because I'm noticing we've got a minus C minus S and a minus C minus S. So if you pull a C1 out of both of these, negative C minus S, and pull a C2 out of both of these, we also get negative C minus S, negative cosine minus sine. So you can then factor that whole group, the negative cosine minus sine, out of both terms, and you're left with, again, C1 plus C2. So we can rewrite the entire bottom term here as negative cosine minus sine times C1 plus C2. And we can do something similar in the imaginary part also. Notice in the numerator here, we've also got two times, not numerator, the top number. We've got 2 times sine times C1 and 2 times sine times negative C2. So if we factor 2 sine out of that, we get negative C1, or sorry, C1 minus C2. And we could also factor the bottom by grouping. If we factor a C1 out of both of these, we get negative S plus C. Factor a C2 out of these, we get S minus C. But if we factor a negative C2 out, we get the same negative S plus C. So by factoring out a negative C2 from these terms, we now have a something times negative S plus C plus something else times negative S plus C. So we can factor that again by factoring a C1 minus C2. Or to put it another way, factoring the negative S plus C out of both of those. And get negative S plus C times C1 minus C2. Any questions on that factoring so far? So making that replacement, we've got negative S plus C times C1 minus C2. And the important thing about this way to factor it is that by writing it like this, every term in this vector has a C1 plus C2, which can be factored out. So that just becomes C1 plus C2 times whatever's left. Specifically 2 times cosine and negative cosine minus sine. And then the pure imaginary part, every term has a C1 minus C2. And this is generally going to happen. When you're dealing with complex conjugate eigenvalues like this, when you split it up into a pure real part and a pure imaginary part, the pure real part will have a C1 plus C2 and everything that can be factored out. And the pure imaginary vector will have a C1 minus C2 and everything that can also be factored out. So I times C1 minus C2 times whatever's left, which in this case is 2 times sine and negative sine plus cosine. And of course, this whole thing also is multiplied by e to the negative 2t. But now that we've got the C1 plus C2 factored out and the I times C1 minus C2 factored out, what happens if you add 2 arbitrary constants together?
It's just the constant.
Yeah, that's just some other arbitrary constant. So let's just bundle those together and say C1 plus C2. Let's just call that capital C1. And same thing here. We've got I times C1 minus C2. C1 minus C2 is some other constant, multiplied by I, which is a constant, and the result is still just some other constant. So let's group these together as big C2. And if we write all that out, and at this point, I think we're pretty much done. So we can re-expand the capital C and capital S into cosine and sine. So we're left with e to the negative 2t times C1 times 2, and we'll fill this in. Capital C means cosine of t, and then negative cosine of t minus sine of t. Plus, and this whole coefficient we're just calling a constant. So C2 times 2 times sine of t, negative sine of t plus cosine of t.
So just to clarify, for that step, you went ahead and bundled I right into C2.
Yes, because C1 is a constant, C2 is a constant, and we don't care what their values are yet. If you subtract arbitrary constants you don't care about, the result is still an arbitrary constant we don't care about. Multiply that by I, the result is still an arbitrary constant we don't care about. And note that multiplying by I doesn't really matter in terms of whether it's real or imaginary, because we didn't really specify whether C1 and C2 are real or imaginary or complex yet either. So C1 and C2 might have been some bizarre complex numbers. We're multiplying them by I, we just get some other unknown complex number. But as long as you've written this in terms of pure real coefficients, like notice that we don't have a times I in any of these anymore. That's really the whole point of all this algebra. Once you've written your solution in terms of pure real values, our general solution, if we now fill in initial conditions and the initial conditions are pure real numbers, then these C1 and C2 you get here will also be pure real numbers, regardless of all the algebra that went into getting there in the first place. So that should be our general solution. And notice that it's got sinusoidal oscillation in both of these vectors. So we've got a linear combination of vectors whose x and y coordinates oscillate, presumably tracing out some sort of circle or ellipse. But we've also got an exponential decay multiplier. So it's tracing out some sort of circle or ellipse that's getting smaller and smaller with each cycle, spiraling in on the origin. So graphs of these tend to be spiral shaped, either spiraling inwards towards the origin if we've got e to a negative power, or spiraling outwards away from the origin if you've got e to the positive t, or e to the positive something t. Any other questions on that? All right, and I know this is a lot of algebra, a lot of work to do here, but it does get easier with practice. So try this out with a few more examples, look for patterns, look for shortcuts, and notice that if you're setting it up this way, then every single time you should end up being able to factor a C1 plus C2 out of the real part and factor a C1 minus C2 out of the imaginary part. So knowing that in advance makes the factoring a lot faster. Like if I had just seen what we started with right away, I wouldn't have necessarily known immediately, oh, I should be able to factor that. But if you're always grouping it together into the pure real vector plus the pure imaginary vector, if you set it up like this, you should be able to factor C1 plus C2 out of the real part and C1 minus C2 out of the imaginary part. So keep that in mind in advance as you're going into this. And simply knowing that you should be able to do that factorization makes it a lot faster. So try that out, get some practice, and I will see you next time.
Thank you.
You're welcome.